Welcome back, everybody. In this next set of videos, we're going to continue to talk about different formulas that we can use with sine, cosine, and tangent. And we're going to talk about the double angle, power reducing, and half angle formulas. So let's start with the double angle formulas. And I have them written out right here for us. So we're looking at sine of twice theta. So again, that would be being plugged inside, right? Which is the same thing as having sine theta plus theta. So the same value being added twice. And the result is 2 sine theta cosine theta. For cosine 2 theta, we get it to be cosine squared theta minus sine squared theta. And finally, tangent of 2 theta is 2 tan theta over 1 minus tangent squared theta. Now, I'm not going to derive these formulas here in the video. You can check out your text for this, or you can even just search online and find those proofs. But what you can do is you can use the sum of the angle formulas that we already learned about. Remember we did sine of alpha plus beta and cosine of alpha plus beta and tangent of alpha plus beta. Well, you can use those formulas, letting the angles be the same, so alpha and beta would both be the same value, and you're able to derive these formulas here from that. So that's where those come from. I want to focus in this video on applying them. So if sine of theta is 5 over 13 and theta lies in quadrant 2, find the exact value of the following. Sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So the first thing I want to do is I do like to draw a picture to start before we hop into the formulas. If you notice here in the formulas, we do also need to know what cosine of theta and tangent of theta are for some of them. So instead of just jumping right in, I want to find those values first. Now, I don't know my exact angle, but I do know it's in the second quadrant. So I'm just going to kind of draw it over here somewhere. So this is my theta. And let's say this is my point xy. And remember, we know that sine of theta is equal to 5 over 13. And if you think back to your formulas, the sine value refers to the y. So this is going to be y, and then that 13 refers to the r. And we can use the formula x squared plus y squared equals r squared to get the x value here. So let's see, we leave x squared, y squared would be 5 squared equals 13 squared. X squared plus 25 is equal to 169. I'm going to subtract 25 from both sides, and I have x squared equals 144, and then x again, taking that square root, would be 12, positive or negative 12. Here we want to be a little bit careful. Notice that because we're in quadrant 2, the x value would have to be negative. So in this case, our x value would actually be the negative 12. Normally we tend to use the positive values, but because we're not in the first quadrant here, we're in other quadrants, we have to be careful about our signs. In the first quadrant, remember, everything is always positive, but that's not true in the other quadrants. So our x value here is negative 12. So because of that, I'm able to actually figure out what cosine of theta is. That would be x over r, so negative 12 over 13. And I'm able to figure out what tangent of theta is, which is your y over x. So that would be 5 over negative 12 or negative 5/12. That would be fine as well. All right, so now let's go in and actually solve the problem. So our formula here is twice, and then we're multiplying by sine theta and cosine theta. So our sine theta is 5 over 13, and our cosine theta we saw was negative 12 over 13. And when I go ahead and I multiply these all through, I have a negative 120 over 169. And this fraction happens to be simplified. I can't do anything else with it. Of course, I would love to simplify that if I can, but I can't. And I'm just using my formula up top here. So I'm just taking this formula right here. All right, so next let's do cosine of 2 theta. So our formula here is cosine squared theta minus sine squared theta. Our cosine value we said was negative 12 over 13. And that's going to be squared. And then our sine value was 5 over 13. And that is also going to be squared. So when I go ahead and I multiply these out, let's see if I can bring it down here. I have 144 over 169 minus 25 over 169, which gives me 119 over 169. So that is my final answer for part E. Now the last one, I think I have to go to a different page for part C, tangent of 2 theta. And again, I'm just using that formula here to plug everything in. So my tangent value here is going to be negative 5 over 12. And the bottom, we are squaring that. So I'm just going to take my time and simplify this. Here, I can actually simplify with the 12s. So if I do take out 2 of each of those, I have 6 left over. So the top becomes negative 5 over 6. And then in the bottom, I have 1 minus, and negative 5 squared is 25, and 12 squared is 144. So I do need to clean up the denominator here. I'm going to use 144 as my common denominator. So I end up with 144 minus 25 over 144. So I have 119 over 144. And then what I can do is I can go ahead and multiply by the reciprocal of the denominator. So I'm looking at here negative 5 over 6 times 144 over 119. And I can go ahead and multiply through. There is some simplifying that we can do here. So I do notice at least, I'm going to cross simplify here. I do see a 6 and a 144. So I can go ahead and at least start there. And 144 divided by 2 leaves me with 72. So if I start with dividing these both by 2, I have 72, and then this becomes a 3. 72 is also divisible by 3, though. So then it becomes 24, and this becomes 1. And now I have 5 times 24, which is 120. So negative 120 is in the top. And I have 119 on the bottom. This is all I can do here. You can change it to a mixed number if you want to, but this is fine. And this would be my final answer. Let's do another example. So we're going to find the exact value of 2 tangent of 15 degrees over 1 minus tangent squared of 15 degrees. Now, hopefully you're recognizing this formula as that double angle formula for the tangent function, right? So this is the same thing as that formula of tangent of twice theta. And the theta here ends up being this 15, right? That's the common angle in both cases. So I can rewrite this. I know that this is the tangent formula for twice theta. And again, my theta here is 15 degrees. So this becomes the same thing as tangent of twice 15 degrees, which is tangent of 30 degrees. And this is a pretty common angle, so our answer here is root 3 over 3. So you can use that formula going in both directions here. You just want to be careful because remember that everything is always twice theta. These are double angle formulas. So if you have 15 plugged in here, then this would have been 30 altogether when you're going ahead and using it. Now there are other forms as well, particularly for cosine. So let me give those to you as well. So you have cosine of 2 theta equals cosine squared theta minus sine squared theta. This is the one we already have. But you also have some other forms. Cosine of 2 theta can also be written as twice cosine squared theta minus 1. And also as 1 minus 2 sine squared theta also. So again, you can kind of go ahead and work this through yourself or read through the text. A lot of it has to come down to that idea of the Pythagorean identity where sine squared plus cosine squared equals 1. So by playing around with that and by plugging in and replacing different things like cosine squared or sine squared, we can get these different forms. So these are just other forms that you can use that may be very helpful. Let's do an example there. Okay, so we want to verify the following identity. Cosine of 3 theta equals 4 cosine cubed theta minus 3 cosine theta here. Now, again, usually we start with the more complicated side here, but this time we're going to start with the left side. Remember that when you're verifying identities, you typically want to pick one side to work with at a time. And what we're going to do here is we're going to use the idea of summing. So this is the same thing as cosine of twice theta plus theta. Now what we're going to use next is we're going to use the sum formula. And we're going to let this be our alpha and this be our beta in the formula. So we're going to go ahead and use that formula here. And just to kind of recap it for you, it was cosine alpha cosine beta minus sine alpha sine beta. And again, we saw this in a previous video. So this becomes, let's see, cosine of twice theta times cosine of theta minus sine of twice theta times sine of theta here. Now we can also do is we can replace our double angles here and use those double angle formulas. And the one that I'm going to use here in this case is I'm going to use the 2 cosine squared minus 1. And if you, I'm going to use that because if you look at your formula here, there's no signs there. So the other two formulas probably wouldn't make sense, right? So how do I know which one to use? Well, the other ones both have signs in them. So my guess is that I'm going to use the second one because if I look at my identity, everything is cosine only. So I'm going to take this piece here and I'm going to replace that. I'm going to replace it with 2 cosine squared theta minus 1. This stays cosine theta. And then I'm also going to replace my sine of twice theta using, again, my double angle formula for sine here. So going back, our double angle formula for sine is 2 sine theta cosine theta. Okay, so that's where those two pieces came up. And now I'm going to go ahead, I'm going to just clean it up a little bit here. So I'm going to go ahead and distribute through. Cosine times cosine squared is cosine cubed. So I have 2 cosine cubed theta minus cosine theta. Here, now I have something to distribute in this part because it's all being multiplied. There's no plus or minuses. So be careful there. I am going to clean up a little bit. I do have a sine and a sine, so those would be sine squared. And then I have the cosine theta. What we can do next, we can do, again, a little bit of substitution here as well, and just kind of keep trying to rewrite and tweak this problem. One thing I want to notice is I do need to get rid of the sine squared. If I look at my original identity, everything is in terms of cosine. And you want to recall, remember, sine squared plus cosine squared equals 1. It's that Pythagorean identity. So if I bring the cosine to the other side, I can see that sine squared equals 1 minus cosine squared. So I'm going to go ahead and replace that piece using the Pythagorean identity. And again, I just want to clean this up a little bit. I'm just going to distribute this part first. So let's see, minus 2 plus 2 cosine squared theta. And that's still times cosine theta. Actually, let me fix this. This minus should be with that 2 there. And then I'm going to go ahead and distribute again. So when I distribute with the cosine, I have minus 2 times cosine theta, and then 2 cosine squared times cosine. So that's where the cosine cubed comes from. And finally, let's clean this up. So I do have cosine cubes here that can be combined. 2 plus 2 is 4. And then these are both cosines. Don't forget there is a 1 there. So -1 and -2 is -3. And finally, we've made it through. If I come back out here a little bit, you can see that we did match the right-hand side. And we were able to use actually quite a lot of different things we've learned, right? We were able to use the sum of angle formulas here. We were able to use double angle formulas. We were able to use Pythagorean identities as well. So a lot came into play to get this identity to be verified. And just remember, you want to use anything in your wheelhouse. We have so many different formulas and relationships between the trig functions now. Anything that works, that we know is true, we can use here. And we just work with one side at a time and just keep tweaking and tweaking and tweaking until we can get it to match, ideally, the other side.